Welcome friends. Now that we have looked at the different macroscopic flow models in both the vehicular and how it can be applied in the pedestrian transport realm. Now let us look deeply into how these different models can be applied for different situations. So in this lecture we will be looking at how the flow models differ by trip purpose, by different types of land uses, how they can have two different regimes in their models. In the models, one regime can be for congested flow and one can be for uncongested flow, and what do we say when a model fits the data well. So how do we determine the fit of a model? We will just quickly look at that. Now we have looked at the macroscopic models, Greenshields macroscopic model, and this is kind of the big picture of those models, where the relationship between speed, directional flow, the speed and flow and density is given by QP is equal to Vp times Kp. So this is something that all of you should remember. Sometimes in case of pedestrians, we also say that we do not use density Kp, instead we use something called pedestrian space, which is just the inverse of density, right. So density is pedestrian per square meter, whereas space is meter square per pedestrian. So just to make it clear, how many people are there in an area per meter square is called pedestrian density, whereas how much space does one person need is called pedestrian space, right. So I need about certain amount of area to move freely in a space. So that is called pedestrian space, meter square per pedestrian. So now when we look at different types of trip makers, right. So everybody who is walking on a pedestrian facility may not be walking for the same purpose, right. Some could be students who are walking to go to school, college, or wherever they are going. Some could be commuters, they are office goers that are walking along a street, whereas broadly another group could be shoppers or leisure travelers who are walking along a street. So it has been noticed that there are some significant differences between these three kind of trip makers along the street. So when you plot this graph again between speed and density, you will see that the students usually have a greater free flow speed, right. So when the density is 0, the speed is called free flow speed. So that means that students usually tend to walk faster, right, and that is faster when compared to commuters or shoppers, and that is intuitive also in another sense that students are usually younger in age. So they would also tend to walk faster, and then you will see that their free flow speed is very different, whereas when it comes to commuters and shoppers, although their free flow speeds are very close to each other, but also they are different because commuters tend to walk a little bit faster as compared to the shoppers, right. Shoppers walk very leisurely, they are shopping, so they are not in a hurry to go anywhere, whereas commuters may be going to their workplaces or going running an errand for their office, so they will be walking faster. So that is what something people many research across countries have shown. Next also now we have seen the macroscopic models for vehicles, where we have seen the relationship between flow and density. But now here if we change the same if we change the graph or the relationship between to see the relationship between flow and space, because remember a pedestrian in pedestrian realm we sometimes use space instead of density. So when we see the graph between flow and space, we notice that as space increases, right. So, need for space. So, I may need little bit over little less than 1 square meter to walk freely, whereas some may need a little bit more than 1 square meter. So, as the space increases, the flow also increases, but the increase is only up to a certain point, right. The increase is maybe just about 1.1 meter square per person. After that, if you keep on giving more space for people, right. So, space is nothing but if there is a person and the distance between the next person, right. This is hypothetically that is the space. Now, if this space keeps on increasing, that means what it in turn it means is that there are very fewer number of people walking, right, because the distance between two people is too much, so much, that means there are overall in the system or in the sidewalk there are fewer number of people walking. So, when there are fewer number of people walking, the flow, which is the number of people per minute per meter, also reduces, right. So, a sidewalk may have a lot of open spaces. A person is walking very freely, yes, they have their freedom to walk, but at the same time there are not enough people to then justify such sidewalks, right. So, you will see many times there are wide footpaths, but hardly any people are walking on that. So, the one person or two people that are walking, they have enough ample amount of space, but the flow, which is the total number of people moving across a certain point per minute, is very less. So, we optimally, you see, just about 1.1 meter square per person is optimal enough to have a very high flow rate. You keep on giving more space to people, actually the flow rate starts to reduce or the flow starts to reduce. So, when we are designing sidewalks, we have to be very careful as to how much width of the sidewalk should be there versus the number of people that are going to walk on that sidewalk. We do not want to give too wide a sidewalk if the volume of people actually who are going to use it is very less, because that will mean that the flow is very low. Flow is very low usually means that you are not utilizing the capacity of that sidewalk to a optimal extent or a maximum extent. Then similarly, the third kind of macroscopic model that we have seen is for vehicles. What we had seen is for speed and flow. Similarly, if you convert it for pedestrian case into speed and space, we see that again similarly, if we keep on increasing the space between for each person, right, space meaning meter squared per person. So, if we keep on increasing the space beyond a certain point, the speed is no longer going to increase, because again what happens is people can walk only at a certain pace, right, a certain speed. They cannot, just because there is too much free space available to them, they cannot walk any faster, because that is beyond their physical ability to walk any faster, right. So, on an average maybe people walk at around 1 meter per second. If you keep on, one may think that, well, let me build a wider sidewalk where I am giving about 4 meter square per person. So, I am giving one person almost 4 square meter to walk comfortably, and you would, and maybe the thought is that if I give more space, the people can walk faster, but it has been noticed that any space more than about 1.5 to around 1.75 square meter does not bring about any increase in speed. However, yes, if the space is less than 1, then there is a much larger reduction in speed. So, when in congested situations, when one person does not have enough space or less than, or space less than 1 meter square for himself or herself, then their speed does get restricted. Okay. So, that is the idea of space, developing a relationship between space and speed versus developing it between flow and speed, okay, which is more of a vehicular relationship, and this is more of a pedestrian relationship, and this is more of a vehicular relationship, right. Okay. So, now the other thing to remember is, in all of these relationships we have looked at say the relationship between speed and density, flow and density, speed and flow, or flow and area space. We have looked at it saying that they are single regime models. So, what do we mean by single regime models is that we assume that the same speed and density relation is valid for the entire range of densities seen in the traffic stream. So, if we say go back to the speed and density relationship, so let us see the speed and density relationship. We are saying that one model, right. So, each of this is a model, right. We can develop a model for the students, this is a model for the commuters, and the bottom one is a model for the shoppers. When I say model, they are all statistical models, right. So, what we are looking at simplistically is to say that even at this density, the slope of these lines is the same at as versus to at this density. So, we are also saying that the slope of this line is constant, be whatever be the density. However, people have found out that there is a cutoff point at certain density where the model has a different regime. So, for example, the slope may be this, whereas after that point the slope may be very steep, right. When you have such a model, they are called two regime models. So, if I can draw the same thing here, if it is a two regime model, what usually happens is that the slope here up to a certain density is this, whereas beyond that density the slope kind of changes. So, then you can make a distinction that these two are both representing the students only, but beyond a certain density they have different behavior. The student population that are walking have different behaviors. So, these are usually called two regime models. And why people are looking at as they become more and more mature in this field, why are they trying to look at these things are, they are saying that if it is an uncongested flow situation. So, there is some density cutoff or threshold at which beyond which the footpath or the sidewalk becomes congested, right. As the density increases, it becomes congested. So, in congested flow, people walk or people's behavior towards walking changes vis-a-vis their behavior or walking under uncongested situation. So, the top part usually is the uncongested situation, right, because here the density is 0, and so you can have free flow speed from here. So, as the density increases, your speed reduces, but beyond a certain density, now it is a congested flow situation. So, this half is a congested flow situation, whereas this is an uncongested flow situation, and your behavior changes. So, what people are now looking at more and more are speed density relation will also be different in different zones of densities, right. They are saying that they are multiple regime densities, two regimes separated, two regime models, they are separated for congested and for uncongested. Whereas, for simplicity of understanding, we have looked so far at all of these models as just single regime model. So, we are not making any distinction between uncongested flow and congested flow. Mostly single regime models are usually used in regular application of these models, whereas in theoretical studies and to improve models, people start looking at two regime models. So, let us so this is an example again, right. So, when we are looking at pedestrian flow and pedestrian density, what some of these newer, so VISIM 1.0, so this is a simulation software, right. VISIM 1.0 at different meters is what they have developed this for, and Fruin was the initial researcher who had developed this model back in the 1970s, and when he had developed it for bidirectional flow, the red line he had made that there is no he had made no distinction between congested and uncongested flow, and he had said that this one model fits the behavior of all the pedestrians, be it on an empty sidewalk or be it in a congested sidewalk. However, when he started looking at unidirectional flows, he saw that, so unidirectional flows meaning people moving in the same footpath, people are moving in only one direction, right. Otherwise, bidirectional meaning on the same footpath they are moving in both directions. So, when you start having that kind of a sidewalk, he saw that if you see the dotted red line, he saw that there are two different models. So, in the uncongested flow, the model kind of goes like this, whereas in the congested flow, the model goes like this, right. So, there are two different models, the dotted dashed lines. Similarly, when VISIM simulations were done using VISIM, VISIM could actually model the uncongested flow pretty well, right, all the black lines you see, but it was not able to model the congested flow pretty well. So, there is essentially people have started to make this distinction as to how there are two different regimes of the same model. Similarly, this is a example of pedestrian flow and pedestrian speed. Again, they have been able to model the uncongested flow pretty well, whereas when it comes to the simulation tools as well as the unidirectional flow, it becomes very difficult to model the congested flow. Okay. Now, why are we telling you about all of these models, right? Why should so much focus be paid towards these models and these relationship between the three basic parameters, speed, density and flow? Because these are utilized to design the capacity of pedestrian facilities. Capacity meaning what should be the width and for how long should you build the pedestrian facility for, right. If you do not know how people move, if you do not know the relationship between the flow and the speed parameters or the flow and the space parameters, then you would not be able to say you would need a 2-meter wide sidewalk for the next 1 kilometer, or do you need a 5-meter wide sidewalk for the next half a kilometer, right. You do not then cannot estimate the right capacity of the sidewalk, and then you make sidewalks that are underutilized or not utilized at all, and that has policy and congestion implications. So, also that is one of the reasons, and then that eventually affects what is called the pedestrian level of service, right. The pedestrian level of service we will get into in the next few lectures classifies how many pedestrians flow for a given width of a sidewalk, for example. One of the ways of measuring pedestrian level of service is to see how much wide width of a facility you have and how many people are flowing through that facility. So, if you do not design it accurately, then your level of service, which is an indication of how well the pedestrian facilities are serving the users, will be affected. So, the basis for everything is to know this relationship between the flow parameters, which in turn tells you to what capacity you should have, you should construct your pedestrian facilities, which in turn affects the level of service that is being provided by the pedestrian facilities. Hence, it is very important that you know about these models. Now, quickly again let us take you through a example of this model and how to solve it. So, given is a u and speed and density relationship along a commercial street with no sidewalk. Okay. So, they have no sidewalk facility, but we have observed that the people that are walking can be modeled using this relationship, right. So, speed has a relationship with a pedestrian density. We have shown you the curves. This is the relationship. Now, the question is asked, what is the average speed of pedestrians when the densities are 0.9, 1.1, 3 pedestrian per meter square? The graphical representation of the model, right, the graphical representation of this model, and derive the other flow parameter models. So, you know that the other flow parameters other than speed and density are speed and flow and density. So, how do you derive that? So, now the first question is to the speed of pedestrians at different densities. So, it is just the very simple, you have the equation. So, you put in the p value the k values and it will give you the speed values. However, the interesting thing to notice again, like you already know by the curve that has been shown earlier, the relationship that has been shown earlier is that as density increases from 0.9 to 1.1 to 3, the speed decreases, right. So, speed for 0.9 is 51.5, then decreases to 48.5 and then finally it decreases to 20. So, this is how usually the relationships are. So, the higher the densities, higher density will accommodate less average pedestrian speed. Now, how do you show it? How do you show it in a graphical manner? So, to show it in a graphical manner, we know that it has an inverse relationship, right? We know, but where does this cut the y axis and where does this cut the x axis? You have to know, correct? So, we all know that the graph cuts the y axis, that point is called the free flow speed. So, at free flow speed what happens? The density is 0. So, if you therefore, mean free pedestrian speed at uncongested condition VPF should be equal to. So, if the density, if you say Kp is equal to 0, then the Vp is equal to 65 meters per minute, which gives you the free flow speed. So, now you know that your first point is here. Secondly, what you know is that the slope of the line is minus 15 times a Kp value, but also what you know is the point at which this curve cuts the x axis is called the jam density. So, at jam density what happens is the speed becomes 0. So, if you put the value of 0 for Vp, this Kp automatically becomes Kp becomes equals to k jam, right. So, if this is 0, you put it as k jam and you know that k jam now is 4.33 ped per meter square. So, now you know your mean free flow speed, you know your jam density. So, you can draw this curve. So, whenever you are told to graphically represent an equation, you have to know all the parameters, all such parameters, so that you can draw the graph. If you do not know this and just draw a graph like this, then we know that you understand that it has a negative slope, but you have not actually calculated these 2 points accurately, and it is necessary for you to do that, right. And then we know how to measure or how to estimate the other parameters of the relationship of the macroscopic relationship, because we know the formula. So, if only Vp is equal, this is given, you convert Vp in terms of q and k, put q and k here, you get the parabolic equation between, now the relationship is between q and k. So, flow and density, which is parabolic, we already know. Similarly, if you convert this into a relationship between q and Vp, that is also a parabolic, flow and speed. Let's convert this into a flow and speed relationship. And now, if you want to convert, don't want to have density, which in many pedestrian cases we do not see the density like that, but see it in terms of space, then this becomes an inverse parabola, right. Why we are telling you all of this is because in the very recent Indo HCM that has come out, these relationships have been depicted for different types of pedestrian facilities. So, if it is a terminal pedestrian facility, terminal meaning it is a end point. So, it is like a last stop or a bus station or something like that. Then the flow density curves are the simplest curve. Let us look at the simplest curve is the speed density curve. The speed density curve is given by Vp is equal to 81.49 minus 21.16. Whereas, if it is if the facility is in a commercial place, so it is a sidewalk going in a commercial place, then you see that the speed density relationship is 64.62. So, immediately what this should tell you is that at terminal places, right, at terminal places the free flow speed of pedestrians is higher than when compared to commercial places, right. In commercial places people will usually walk slower, maybe there are maybe there are shops where they are shopping. So, the commercial areas, and usually the number of people in the commercial areas walking is also high. So, the speeds may be low, and hence the free flow speed is lower than in case of terminal spaces and terminal facilities, where people usually have got off a bus or got off a metro rail, and then they want to walk pretty fast, right. They want to get to their homes or offices or something. So, that is the easiest relationship to be understood. So, here our ENDO-HCM also develops different models for different types of land uses, right. So, you see that there are these 1, 2, 3, 4, 5. There are 5 different land uses for which these models have been developed: recreational land use, terminal land use, institutional land use, commercial, residential. So, when I say land uses, so it is the land use that is abutting this facility, right, or the land use that is containing this facility. So, if recreational land use, meaning maybe it is there is a footpath that is alongside a park, for example. Terminal, we just told you. Institutional, meaning maybe there is a big office building or a big school or a big college, some kind of institution, there is a sidewalk along it. Commercial, meaning again market area. Residential, meaning near your homes. So, it has been seen that people behave differently, right. We showed you earlier also, if you are a student versus if you are a shopper versus if you are a commuter, your behavior is different. It is furthermore, it has been found that if the sidewalk is along different types of land uses, people behave differently, right. So, you see that the green one, which is the recreational model, sorry. For the recreational model, you see the slope is very gentle and the free flow speed is much less than for the others. That meaning that people usually want to walk very leisurely, very slowly along footpaths that are closer to recreational facilities or abutting recreational facilities, whereas if there are other ones, they walk usually faster than that. That is the relationship. Similarly, the other relationships are depicted here. Now, whenever people want to know how good is the model that you have developed, what people usually try to mean is to calculate what is called an R squared. So, these are all simple linear regression equations, right, not simple, I mean linear regression equations. So, for linear regression equations, what usually they want to see is a trend line like this, right. Is there a trend line that explains all of your data set? So, these may be all of your data set, relationship between x and relationship between x and y, right. So, these may be all your data sets, but is there a common trend line that can explain the behavior of majority of them? So, that trend line usually the higher the R squared or the R squared closer to 1, if the R square is closer to 1, then you usually say that that model fits your data very well. So, R square can be, the model can be it can have a negative slope or a positive slope, does not matter, it could be like that also, but if it is closer to 1, now in this case it is saying it is equal to 1, which also sometimes is not very good, because it might depict that you have done something with the data set and removed outliers, which maybe are important for your situation, but you have removed them and you have got a perfect fit, which is always not good. You have to always work towards R squared should be tending towards 1, that should be your goal. It should not be not necessarily be equal to 1. And if it is something like where there is no relationship, then you have to look at other types of models which can explain your data, right. If there is no relationship between x and y, then it is no linear relationship between x and y, then you start looking at other kinds of models. Okay. So, R square is the goodness of fit index. So, that is all about the flow models for this lecture. Again, the references are provided. So, in conclusion, what we have looked at is the macroscopic modeling of flow models using space particularly, but also using the other 3 parameters. We have also looked at how for different land uses or for different trip purposes the relationships vary, and we have introduced you to this terminology called R square, which is a judge of how good your model is performing in relationship to the actual data. Okay? Thank you.